Thanks for having me, Tim, and hello, everyone. I'm really excited to be here. It's my first time at age 50 attending a conference and meeting a like-minded group of hobbyists, experimenters, engineers, physicists, and enthusiasts who share an interest in extraordinary alternative propulsion energy technologies. Public speaking isn't my strongest skill, so I would like to apologize in advance, but let's see how it goes. Please follow the Zenodo link at the left bottom side of the slide if you would like to download the presentation itself and the walkthrough in case you are interested in. I'm originally from Greece and hold a degree in electronics. I worked for about 5 years as an electronic engineer in a small company in Athens, and later worked for about 17 years here in Switzerland as a software system test engineer, and right now I'm unfortunately unemployed. What has always inspired me, even since childhood, is a fascination with extraordinary technologies. That same curiosity still drives me today to explore them and work with them creatively. My journey began in a more systemic way when I bought my first PC around 1996. One of the first things I did was search online for patents, websites, online forums, and papers about unusual technologies in alternative propulsion and energy. By around 2000, I came across with Tim and others through Yahoo groups. I believe there was more interest in these topics during the 90s and the early 2000s, so I might be wrong. The theory I'm about to share starts with classical mechanics and expands to electromagnetic, gravity, and the consistent extension of special relativity. It also includes proposed experiments to test these ideas, as well as a demonstration I recorded back in 2009. Over the past 20 years and even more, I repeatedly explored, released, and later removed part of these ideas and a couple of experiments on personal websites and in papers, though at the time they were based on flawed concepts and mathematics. Still, my intuition kept telling me that there was something real behind it. The first slide shows the destination of this presentation, actually, but the real question is, how do we get there? So the best way is to start with something familiar, classical mechanics. So when we talk about propellant-less propulsion, we are really asking whether an isolated system, one not influenced by external forces, can gain momentum through internal means. And to separate the idea of a reactionless drive, which is impossible by definition, from a self-contained system, an isolated system. That distinction eventually showed me why the term reactionless was used through the years. In the drawing, two counter-rotating orbiting masses orbit along a cyclic path. The linear inertial action and reaction, according to Newton's third law, always cancel out. But when one mass moves clockwise, the rest of the system gains counterclockwise angular momentum. Here we speak not about linear momentum, but about angular momentum. When the other mass moves counterclockwise, the system gains clockwise. The system gains clockwise angular momentum. If both orbit symmetrically, the net angular inertial reaction cancels to zero. And that is, I believe, the reason about that is also may justify mathematically why it was called through the years as a reactionless drive. Here we speak that the angular reaction of the system is the net angular reaction of the system goes to zero, but the inertial forces still exist, but they are balanced each other. They balance each other. That's the idea. As a result, the isolated system expected to be propelled only by inertial angular forces, since the angular inertial reaction is effectively zero, as we just mentioned. The expressions on this slide and on the next one are rigorously derived from classical mechanics. The full derivation is included in the first section of this work. Over the years, I tried many times, but without success, to find a rigorous online derivation derivations that included angular components to show whether an isolated system could be propelled by internal mass. Most derivations relied only on Newton's third law, using collinear forces as justification, and often misunderstood the challenge itself. As a result, they completely failed to account for the role of angular components. Yeah, okay, exactly. Yes. The main result of the derivation that it includes, oh, sorry, I think I went, no, it's number 3, no, it's okay. The main result of the derivation is that it includes tangential force or acceleration. If you ask most physicists or online forums about this, they will immediately respond that this is nonsense. If your model includes tangential acceleration or force, it means external forces are acting, so the system is not isolated. In my view, this is a misunderstanding in mainstream physics, though I could be also wrong. I'm not a physicist, I'm just an engineer, but yeah, I will explain later about this. From my perspective, an isolated system means that all power and force generation occur entirely within the system frame itself. Mainstream physics still resists this idea, largely because of how tangential acceleration is defined in textbooks. In the force expression, we see two terms that together account for the total action force. The first is the net centripetal force along the y-axis, a Bowden force that sustains the orbiting motion. The second is the net tangential force, shown here along the x-axis, which represents the real thrust force. Okay. So at first glance, this may seem incorrect. You may seen some YouTube videos that the propeller's propulsion appears on the y-axis. That needs to be discussed later if anyone is interested about it. That is partly true and partly not, as I will explain next. If angular velocity is constant, for example, the phase second derivative is 0, only the net centripetal force remains. The system simply oscillates along the y-axis around the center of mass, and in outer space it would never gain momentum. This is the case when we don't have tangential acceleration and only centripetal. The other illustration shows how real thrust can be modeled in terms of changes in system's inertia as long as the orbiting masses experience tangential acceleration. The system behaves as though it has reduced inertia, which in turn leads to acceleration of the system as a whole. Okay. Yes, exactly. So now that the inertial drive model has been introduced, let's consider how a mechanical version could work. In this setup, two orbiting masses move in parallel planes. This arrangement lets them orbit continuously with angular velocity, constant or varying, controlled by phase modulation. The outcome is sustained thrust in one direction. At first, standing waves may seem unrelated to a mechanical inertia drive, but if you look closer, each orbiting mass acts like a sinusoidal oscillation along the y-axis. Moving in opposite directions, they resemble two sine waves on the same line that combine into a standing wave. Yuri Nikolai Ivanov's work uses a simple trigonometric function and observes that the nodes can move along the x-axis, along with an entrapped mass when phase modulation is applied or when angular velocity or frequency changes. That observation is valid. However, such a system cannot produce acceleration of the whole system because the action is linear, and this is my view. This produces a collinear reaction throughout the rest of the system, consistent with Newton's third law and the conservation of momentum. Consequently, a non-moving standing wave reflects the situation in the mechanical inertia drive where two orbiting masses move with constant angular velocity, producing no real thrust along the x-axis. When phase modulation or change in angular velocity is introduced, the standing wave gains acceleration and its nodes shift along the x-axis, mirroring the behavior of the mechanical inertial drive. Regarding the mathematical expression shown, this work derives tangential acceleration from the curved path followed by the orbiting masses. By contrast, Yuri-Nikolai-Ivanov's approach, though based on trigonometric functions, seems to assume curved paths only implicitly and derives his acceleration expression from the standing wave itself. The aim here is not to compare the two theories, but to acknowledge Ivanov's idea and to incorporate the concept of moving standing waves into our framework while explicitly introducing the requirement of curvature. As we will see in the following slides, we propose using moving standing waves as massless entities with confined energy that, when accelerated, exhibit inertial effects, an aspect not addressed in Ivanov's work. Furthermore, we will show that moving standing waves are central to both the acceleration and the shielding mechanisms of the inertial warp drive, which will be introduced at the end of this presentation. To understand how our model behaves, before attempting a real mechanical inertia drive, you can run simulations such as the one shown here. In this idealized case, the resulting thrust along the x-axis appears as a rectified waveform. It approaches zero, but never becomes negative. Compared to the net centripetal force, the tangential force is about 4.6 times greater. To reach this efficiency, angular velocity must cross zero and reverse, as shown by the Kian dust curve. In practice, I have never seen this done, likely because controlling large one-direction acceleration is difficult. Sustained thrust would require repeatedly reversing the orbit. Holding constant velocity, slowing to zero, then switching direction. That demands precise timing and not only. Another reason why such implementations do not exist is a common misconception, which will be addressed in the next two slides. I'm really awful in presentation, I know. Anyway, this simulation reflects, so we are on slide 6. This simulation reflects how most implementations should work, though in reality they appear to fail. To keep the orbiting masses moving in the same direction, one clockwise and other counterclockwise, with reversing their motion to achieve thrust in one direction, for example to the right, we introduce an angular velocity offset and adjust the amplitude of the phase modulation. These two parameters are tuned to maximize efficiency along the thrust axis, resulting in equal magnitudes for the net centripetal and tangential forces. As shown, the angular velocity nearly touches zero, but never becomes negative, ensuring that the orbiting directions remain unchanged. Okay. So here, this slide highlights the mistuning in mechanical inertial drives developed so far, in my view. In YouTube demonstration of these propelled systems with rotating masses, thrust is usually assumed along the y-axis, while I argue the true thrust axis should be the x-axis. The misunderstanding arises because experimenters lacked a guiding theoretical model relying only on classical mechanics and direct observation. To maximize thrust without reversing the orbiting masses, current designs rely on two assumptions. Thrust is directed along the y-axis, while the x-axis contributions are cancelled with rollers constrained to the y-axis, or any small x-axis motion intentionally suppressed as it cannot be utilized. And increasing angular velocity enhances the centripetal force, which is often mistakenly referred to as centrifugal force. We know that the centripetal force reflects bound motion. So how do these devices seem to accelerate? They simply exploit surface friction, which breaks the action-reaction symmetry. Friction acts like a hysteresis that disrupts the principle. Secondly, you may have noticed that such devices accelerate briefly and then decelerate almost immediately, ending with only a small final speed that doesn't match the cycle's apparent acceleration. This effect is not caused by friction. Instead, it shows that the motion is bounded and the device is mistuned. Put simply, such devices will never achieve sustained acceleration in outer space, again, according to my view. Okay, test one, yes, simulation, yes. The test shown on this slide is a proposal not exactly with extreme simulation values presented, but intended to introduce what we later call the benchmark velocity in the validation protocol. There is a validation protocol later in the slides that I'm going to present you. In practice, to qualify a device as a genuine mechanical inertia drive, it should be tested in a lubricated corridor that should achieve at least twice the velocity gain during the first cycle by the end of its translational motion along the corridor. I have always been interested in finding online simulations or calculations that show that what would be required for a mechanical inertia drive to overcome gravity, but I never came across any. Using the model I developed in my work, I decided to attempt the calculations myself by adjusting the frequency. As you see, I have set 15.91 Hz on simulation 2. And assuming the entire system has a mass of 1 kilogram, the results suggested that it could, in principle, float in mid-air. The challenge, however, lies in the mechanical integrity of the system. The orbiting masses would need to reach acceleration about 10 times greater than gravity, far beyond the current capabilities of mechanical actuators, which are typically limited to around 1 G. Although mechanical devices were never my main interest, I would encourage experimentalists or anyone curious to try building a small mechanical inertia drive with or without microcontroller-based control of angular velocity to test the claim about the true thrust axis. I don't suggest this is a way to validate my own work. I honestly don't mind. But if someone succeeds in replicating the claim, according to my view again, they will have in their hands a genuine model for all types of inertial drives, including electromagnetic versions with massless entities such as confined energy from standing waves or fields. Okay, we have now worked through 9 slides and arrived at the more serious material. The earlier slides were essential. They built the foundation for seeing how the model can be transformed and applied to electromagnetic devices. Here, the orbiting masses are replaced by standing waves that confine electromagnetic energy. As in the inertial drive model, we have both clockwise and counterclockwise guides in this case. I carry out some calculations to outline a relative feasible construction using 2 gigahertz propagating microwaves with a confined energy density about 10 joules per cubic meter. By applying an angular velocity shift equal to half of the base angular velocity, the system is expected to accelerate along the x-axis with a force of 6.7 Newton. For an isolated system with a mass of 1 kilogram, this corresponds to an acceleration of approximately 6.7 meters per second squared. Another rather unexpected result is that the corresponding energy density behaves like a massless object exhibiting inertia equivalent to 3.66 multiplied by 10 to the 4th power in kilograms, but it's massless, with an acceleration of about 91.5 micrometers per second squared. Multiplying these values gives a maximum thrust that is twice the 6.7 Newton. How can that be possible? These questions also troubled me while writing this paper. Initially, I thought the wave itself was responsible, but I now believe that was incorrect. What actually induces acceleration and produces inertial effects transferred to the rest of the system is not the wave itself, but its confined energy. Therefore, the induced inertial effects and acceleration must be calculated with respect to the confined energy. Along the same lines, this experimental setup was, believe it or not, partly and even accidentally recreated back in 2009. I will talk about that in the next slide, and also show you the recordings of the experiment itself. Instead of using toroidal waveguides, this experiment uses manganese, zinc, ferrite toroidal cores with their specification shown in the table. The standing wave that forms is mainly magnetic and interacts with the dipoles in the ferrite core. This creates what I would call a bulk magnetopolariton, but I don't expand at all, theoretically in the paper about this. As an observation, just I have put it in the paper. Basically, a mix of the field and dipole working together. The calculated frequency comes out to about 4.96 kilohertz, which matches closely with what's seen on the signal generator. However, this is outside the normal range of the material, since it is usually meant to work best between 20 and 200 kilohertz for power transformers and inductor applications. In other words, you cannot use 4.96 for power transformers and inductors, but you can use it to demonstrate such kind of effects, as I will show you later. Here again, we see that each bulk toroidal magnetopolariton has an equivalent electromagnetic mass of about 0.4 kilogram, which is quite close to twice the mass of one toroid. The one toroid, if you see the table, the mass of the toroid is 0.2 kilograms, which corresponds to an acceleration of 0.58 meters per second squared. Both values come directly from the energy density rather than from the wave parameters themselves. When we multiply these values together, we obtain again the maximum thrust. Okay. We now arrive at a slide that could represent either a paradigm shift. We speak about an EM inertial drive or primitive inertial warp drive, I would say, or a delusion. Maybe it's nothing. The background is this. Back in 2009, while studying the work of Professor Fran de Aquino, I attempted to measure the propagation velocity of the electromagnetic waves through a manganese zinc ferrite core using a very low power. My attention, however, drawn to the noise produced by magnetostriction, the slight expansion and contraction of the core. When I placed the ferrite core on the floor and applied more current without limiting the resistor, if I recall correctly, it suddenly moved with strong energetic motion in a diagonal direction with manually increasing frequency. The ferrite core's apparent self-propulsion was a shocking moment, unlike anything I had witnessed before, even though the first test in the YouTube video, as you are going to see, demonstrates a reaction that is about 5 to 10 times weaker. At that point, the material began to decline in its response. Fortunately, I managed to capture 3 different recordings. When I shared them on the NASA spaceflight forum some years ago, they were skeptical. Some claimed it was a hoax using hidden magnets. Others suggested I was moving cables off camera, or that it was simply vibration interacting with the table. A few even said, suspend it and see if it moves, which I tried, but unsuccessfully. Everyone who commented focused only on the first experiment and overlooked the other 2. The truth is that the material is extremely sensitive to current changes at frequencies below its allowed range, so it doesn't behave as one might expect. To see a proper response, one would need a fresh material rather than the degraded one I used. About 4 years ago, I shared both a theory covering various topics and the experiment on YouTube, but while I later removed the theory, I chose to keep the experiment available. As you are going to see in YouTube, is about 4 years online. So the first experiment you will see shows the ferrite core moving diagonally across the table's surface driven by friction, a tangential force without changing the frequency. It's a special condition that was discovered accidentally, achieved by periodically increasing and decreasing the frequency until the ferrite appears to settle into a log state. So here we go. I hope it will work. Oh. Okay, the second experiment involved a Lego car with a ferrite core placed on its back, knowing that the force was tangential and that the material had already begun to degrade. I attempted amplitude modulation using a modulation signal of 100 millihertz. The goal was to illustrate a situation similar to trying to push a car while riding inside it. Oh, when I click, it stops maybe. I don't know why. Okay. It's very short anyway. And the third experiment focused on controllable rotation. Around 2009, or perhaps a year earlier, I came across the work of Yuri Nikolai Ivanov on rhythm dynamics. I wondered whether I could demonstrate controllable clockwise and counterclockwise acceleration of a standing wave along a curved ferrite path, thereby supporting Ivanov's claims about moving standing waves. At that time, I hadn't yet developed my own theory, and it was mostly influenced by Aquino's work, which seems to contradict my observations, particularly regarding the high frequencies compared to what one of his papers suggested. In this video, you can see that when I increase the frequency, the toroid rotates clockwise, and when I decrease it, it rotates counterclockwise. Oh, sorry. So you see here, it's 5.18 kilohertz, the signal generator. The calculated force is about 0.24 Newton. For a mass of 0. kilogram, the normal force is about 1.9 newtons. With a static friction coefficient of 0.3, the force required to overcome friction is 0.58 Newton, nearly 2.4 times greater than the calculated value, even if we take the maximum force, possible force, which is about 0.488 Newton, it is still about 1.2 times smaller than the 0.58 Newton needed to overcome static friction. This suggests either that the static friction coefficient is less than 0.3 or that the actual force produced is greater than the calculated value. Although the deviation is relatively small, even under assumed ideal conditions, it's an encouraging result suggesting that the theory is on the right track. But again, you never know. For those interested in replicating the experiment, the material costs about $38 to $40. If you already have an acoustic amplifier rated at 40 watt RMS or higher, I use approximately 70 watt RMS for a 4 ohm load. You can wind 3 to 4 turns of wire around the ferrite to achieve an inductance of about 1 millihenry. For experimentation, it is advisable to include an inline resistor of roughly 4.7 ohm, and that can withstand about 150 watt, and to avoid using capacitors for resonance. The manganese zinc ferrite used here is not suitable for practical applications, but serves well for demonstration. I would welcome feedback from anyone who attempts to replicate the experiment. With the right laboratory setup, other ferrites or even iron cores could be tested. Using a pair of such materials might reproduce the inertial drive model electromagnetically and suggest a promising propulsion concept for space, at least in its early stages. As a side note, it remains unclear whether anchoring the rotating core iron or ferrite would transfer the generated momentum through the accelerating standing wave to the rest of the system. This aspect of the theory hasn't yet been experimentally verified, although the second experiment with the Lego car appears to support it. Okay, here we have the protocol. The findings of this theory allow us to establish a validation protocol to determine whether a candidate device qualifies as a genuine inertial drive. We don't need to cover every detail here. What matters is the main criterion. The device must produce real thrust perpendicular to the excitation, and if the device is treated as a black box, it should demonstrate at least twice the initial acquired speed by the end of a long lubricated corridor. As you may understand, and as I said, earlier, the most mechanical, at least the most mechanical, they do not comply with this validation protocol, which is a very good, I think we could discuss it, later or even offline with anyone, interested about it. So we go on this next slide. Okay. I included a special section as an attempt, not a full examination of Podkletnov's gravity shielding experiment. My goal was to see whether I could describe the experiment using the framework I have developed so far, applying certain known parameters and making a few assumptions. In the experimental setup, the rotating superconductor gradually decreases its angular velocity according to Podkletnov's parameter values. Under those conditions, a nearby 1 kilogram mass showed a maximum weight reduction of about 2%. I used 2.4% in my analysis. What happens is this. A pulse generates circumferential supercurrents, and in the superconducting state, the Meissner effect expels the magnetic field from the superconductor, creating a poloidal-like topology as illustrated. The rotating poloidal magnetic field together with the induced motional electric field resembles a mechanical electromagnetic standing wave. While the disk undergoes controlled deceleration, the mechanical electromagnetic standing wave accelerates in the opposite direction, transferring momentum or an inertial field into the surroundings through the accelerating confined energy. Once again, we see that the confined energy behaves as if it has an effective inertia of about 3.83 milligrams, with a corresponding acceleration of roughly 2.05 multiplied by 10 to the second power meters per second square. These counterintuitive values clearly require further investigation and control experiments to confirm their validity. With the assumed reduction in weight and the calculated thrust, the energy density comes out to about 2.9 joules per cubic meter. After running the numbers, it looks mechanically feasible to achieve a deceleration lasting around 39.5 seconds. During that time, the system's weight would drop to about 2.4 of its original value. Another unresolved issue is how the setup generates an upward thrust or inertial field once the energy is confined around the circumference. One possible explanation is that the vortex forms when poloidal magnetic field lines couple with azimuthal motion, though the exact mechanism is unclear. Podkletnov suggested this effect might be explained by vortex theory, but that's not something I cover in my work. Up to this point, we have seen that confined energy with standing waves, when accelerated or decelerated, can transfer momentum to its surrounding. Neutral mass may interact with this momentum, resulting in either in acceleration or in apparent reduction of weight, depending on the direction of the force produced by the confined energy. This raises an important question: does the translation of confined energy exhibit gravitational-like or inertial-like field properties? In this section, I present what may be the simplest derivation of the coupling between electromagnetism, gravity, and inertia. By equating the thrust force derived from electromagnetic parameters with an equivalent gravitational or inertial thrust force, or by equating the corresponding energy densities, we can establish a theoretical link: electricity with gravity and magnetism with inertia by analogy. Setting the gravitational permittivity equal to 4 pi multiplied by the gravitational constant, we can then derive its counterpart, the inertial permeability, in analogy with the magnetic permeability of electromagnetism in Maxwell theory. Furthermore, by defining electromagnetic mass and integrating it with the new expressions dg and di, these two have Newton per kilogram or meter per second square as the units of these two expressions. We arrive at the concept of the electrons or positrons' effective massless electromagnetic mass. Remarkably, when this electromagnetic mass is divided by Planck's mass and squared as a ratio, it unexpectedly yields the fine structure constant. I'm very awful. I think it was a bad idea to make a paper. Anyway, I couldn't leave this out of the presentation since it directly relates to the link between electromagnetism and gravity. The link at the bottom, titled Hidden Geometries in Maxwell's Equations and the Force Flux Route to Unified Static Fields, builds on a work I developed a few months ago following an earlier paper titled Classic Unification of Electromagnetism and Gravity. In fact, the paper extending Maxwell's equations should have carried the unification title, but the idea only emerged later. A physics journal reviewer of the first paper rejected it, saying he saw no connection between my proposal and Maxwell's equations, since I was discussing gravitational charges using the concept of a general gravitational potential. That comment made me think, why hadn't I considered Maxwell's equations from the start? So I began writing the new paper, and during the process, I discovered an expression inspired by Gauss's field flux, the first of the 4 Maxwell equations. In my view, if Maxwell, around 1860, had introduced a force flux law, it wouldn't have described a new field, but would have allowed him to replace electromagnetic constants such as electric permittivity and electric charge with gravitational permittivity and gravitational charge. The result would be the same Coulomb force, but now expressed in terms of gravitational parameters. In that speculative framework, Maxwell could have uncovered a link between electromagnetism and gravity, even though no experiments at the time were available to confirm such a connection. This work suggests it calculates the existence of 3 additional emergent charges associated with the electron itself. How can that be, you may ask, given that the electron is treated as a single purely electric entity? Consider a spinning electrically charged metallic spherical surface. The motion of the static charges generates azimuthal currents, which in turn produce a magnetic field. That magnetic field can be understood as an emergent magnetic dipole charge, which disappears once the rotation stops. By analogy, gravitational and inertial charges could also arise as emergent entities created through the acceleration or deceleration of a spinning electrically charged metallic sphere. Ultimately, this work derives through a Maxwellian approach the link between electromagnetism and gravity, yielding the same electrogravity and magnetoinertia expressions shown earlier. In simple terms, changing the polarity or direction of electric or magnetic field can create a counter effect, an anti-gravity response that opposes Earth's field lines, producing a locally weaker gravity zone or even reversing them. By integrating a Lorentz-like field into Maxwell's equations and combining it with the force flux law, we obtain an expression resembling the Lorentz force, but now describing the unified field, for example, of the electron. In practice, if we select electromagnetic constants, we recover the electron's total electromagnetic field. If instead we select the gravitoinertial constants, we obtain its total gravitoinertial field. Here, the gravitational field is expressed in units of kilogram per meter per meter. That means, if you in place of volt, we have kilograms per meter, the gravitational field, the units. While the gravitational displacement field is measured in meters per second squared, as illustrated in the plot. At a distance of 0.12 nanometer, the electric field is approximately minus 1.13 multiplied by 10 to the 11th power volt per meter, while the gravitational displacement at the same distance is minus 9.81 meters per second square, equivalent to minus 1 G. I chose to plot gravitational displacement rather than the gravitational field itself, since its units and magnitude is more familiar and directly relatable to our everyday experience of Earth's gravity. Something I have written in an older paper that I didn't include or even removed in any of the papers I have released so far, and this is because a reviewer was disagreeing with my proceedings and said that it was wrong and disregards the Casimir force. I believe the second part of the electron total field seems to have to do with the Casimir force. Thus, quantum fluctuations shouldn't have any relations with the force in general, again, according to my view. In 2004, physicist B. V. Ivanov, it's not the same Ivanov as in the beginning. This Ivanov is from the Institute for Nuclear Research and Nuclear Energy in Bulgaria, published a paper on the link between electromagnetism and gravity, which he called root gravity. His work produced the same formulas using natural rather than SI units that predict the exact electric field and magnetic induction needed to generate 1G. In the discussion section of his paper, Ivanov points out that the connection between electromagnetism and gravity could have been identified many times, 8 times, in fact, over the past 80 years, counting from 2004. His approach relies on advanced mathematics such as tensors, general relativity, and WMP, Well, Mayum-Dar, Papapetrou, space-time solutions, while my proposal uses only high school level math applied to classical electrodynamics and Maxwell's equations. Okay, in this work, I include a section on the Alcubierre warp drive, not to introduce a new metric, which I'm not capable of doing, but to examine the energy requirements using specific values and later compare them with my proposed inertial warp drive concept. For this purpose, I use an energy scaling estimate expression. It is dimensionally correct, though not an exact solution, and I expect to remain within an order of magnitude of the true result. Importantly, it doesn't assume a specific bubble geometry. As shown for the chosen parameter values and a bubble thickness of 1 meter, the energy requirements are enormous. As a teaser, I suggest the possibility of using electromagnetic fields to create massless inertial fields that could achieve the same goal without distorting space-time. However, as we will see in the following slides, the electromagnetic energy we speak about, the confined energy associated with massless electromagnetic mass, cannot be equated to rest energy as described by Einstein's famous relation mc square, which reflects the conversion of annihilated mass into energy. And finally, we arrive at the ultimate destination, the inertial warp drive. In this concept, an inertial shielding effect is incorporated into Minkowski metric, the so-called flat space-time, through the reduction of the local propagation rate. This effect arises from a pair of counter-propagating accelerating standing waves, which essentially isolate the system's inertia from the rest of the universe. This is an assumption, of course. The velocity of the system is determined by the net tangential velocity of the standing waves. In this framework, the system's mass is not its bare mass, but an electromagnetic mass, similar to the magnetopolariton concept. Put differently, the system's mass doesn't exhibit ordinary inertial properties. Instead, it reflects an electromagnetic inertia that can be controlled through time-varying phase modulation. As a result, the system energy is no longer governed by Einstein's relation mc square. The concept of the inertial warp drive requires a broadening of special relativity, which I term inertial relativity. In this framework, special relativity becomes a subset that describes relativistic motion driven by external forces. The three plots illustrate how relativistic inertia, velocity, and momentum behave in comparison with both the broadened framework and classical special relativity. In inertial relativity, inertial can reach a minimum of 0, producing a transparency effect where the system becomes essentially undetectable. Velocity, on the other hand, may cross and even exceed the speed of light barrier, since the final velocity depends on the amount of confined energy available per cycle. Finally, momentum in inertial relativity rises to a maximum value before decreasing back down to 0. It's worth noting that when we set ns equal to 1 in the new relativistic inertia expression from inertial relativity, we recover the formulation of Dr. Carezani, an Argentinian physicist who introduced autodynamics around 1951. Although Carezani didn't invoke inertial shielding, his approach of reducing inertial frames leads to an outcome that coincides with the inertial frame aligning with the wave field. Another important observation is that all tachyon or superluminal propagation theories that treat C as a strict lower bound. In both special relativity and these theories, there is a discontinuity at the velocity equal to C. In contrast, inertial relativity and Carezani's relativistic expression do not exhibit such a discontinuity. A possible technical approach, so it requires special materials is the use of surface waves, similar to the ground waves employed in long wave radio communication, which follow the curvature of the Earth. In this case, the inertial warp drive would operate with surface standing waves, most of their confined energy lying outside the spherical shell, yet still capable of accelerating by following the curvature of, for example, of a spaceship's hull. When we apply the same parameter values used for the Alcubierre warp drive to the inertial warp drive, treating the bubble dimensions as a spherical shell of equal radius, we uncover a working frequency of 238.8 kilohertz, which lies in the long wave radio spectrum. Because standing waves can never be perfectly confined, some energy will leak into outer space. This leakage could be used to identify the propulsion or shielding frequency, or even estimate the spaceship's dimensions with a custom software-defined radio receiver. I added this. What I'm going to address is something that I don't include in my work. I put it here, as a teaser for those who would like to explore this as a project. So the idea is the following. If extraterrestrial spaceships use this principle as the inertial warp drive, their propulsion and size might be detectable, though, as with any radio receiver, distance and sensitivity remain central. By directly converting the received signal without demodulation into digital data, a deeper investigation becomes possible. Based on the findings of this work, the inertial warp drive is expected to operate by changing the angular velocity of standing waves. This creates a frequency shift similar to FM modulation, but without a carrier. While such carrier-less FM isn't possible in a radio broadcasting, it's comparable to SSB single-sideband AM, where AM modulation without a carrier is feasible. For spaceship objects with radii between 1 and 1,000 meters, the working frequency of a single standing wave for propulsion or shielding is expected to fall between 80 kilohertz and 80 megahertz as carrier-less FM modulated signal. What I found extremely interesting is that the terrestrial radio broadcasting band from 80 kilohertz to 80 megahertz uses AM modulation, not FM. So if we capture signals in this band and convert them directly into digital form without first demodulating, we can store this data on a PC. Then by applying software-based digital signal processing, we could filter out the AM content and scan for frequency shifts. Virtual carrier through the processing software, we could even demodulate carrierless FM signals, opening the way to detect otherwise hidden modulation patterns. It would resemble hunting for ghost-like SSB FM signals, which in reality, they do not exist. But if these spaceships use this principle as the inertial warp drive, there is a good chance that we could probably receive such kinds of signals. So besides the frequency shift, both shielding and speed are proportional to the confined energy. This means the carrier-less FM signal could reveal speeds only up to the speed of light, but not beyond. For the same frequency, the final velocity may fall below or appear above light speed, as shown in the work through the NS energy factor. I imagine such a detection setup could work like a non-rotating passive radar antenna that only receives signals, like a typical radio. For now, this remains speculative, but as I wrote this presentation, I became so absorbed in the idea that it struck me as an exciting and fully feasible exploration project, combining RF electronics, ADC conversion, PC-based signal processing software, and machine learning algorithms for automatic detection. It would be a thrilling moment if at an upcoming APEC conference, someone presented the equipment as also genuine, not faked recordings of signals that might be coming from potential extraterrestrial spaceship sources. Such a discovery could mark a new chapter for the conference itself. So returning back to the presentation, the expressions linking gravity and inertia with electromagnetics allows us to calculate the required energy density. From this, we can determine the energy needed for a spaceship of given dimensions to accelerate almost instantaneously within 4.18 microseconds from rest to 10 times the speed of light. By considering the electromagnetic volume through which the standing waves propagate, we arrive at an energy requirement that is many orders of magnitude lower than the estimate derived from the Alcubierre warp drive. The inertial warp drive section concludes with an attempt to reconcile Alcubierre's energy requirements with inertial cell dynamics. Put simply, the question is, what must change in the Alcubierre warp drive model for it to become an inertial warp drive? Instead of warping or distorting space-time itself, the inertial warp drive applies a warping or bending of system's inertial response, achieved by influencing the local propagation rate through electromagnetic means. By multiplying and dividing with 4 pi and the square of the wave period, we can transform the energy requirements of the Alcubierre energy estimate. Two adaptations make this possible. First, we define the velocity to time ratio as the tangential velocity of a single standing wave rather than the pair. Second, we replace the thickness with the product of the speed of light and the wave period. This substitution allows to be re-expressed as an electromagnetic volume. While calculating the equivalent electric field strength associated with the required energy density, we find that it exceeds the Schwinger limit, the threshold at which the vacuum becomes nonlinear. It begins producing electron-positron pairs, according to quantum electrodynamics. This implies a natural limit to acceleration, roughly one-third the speed of light per second. That is equivalent to 11.6 million times Earth's gravitational acceleration. In addition, this poses an energy density limit for confined energy that must not exceed approximately 1.5 multiplied by 10 to 25th power joules per cubic meter. A big unanswered question is how the spaceship keeps moving once phase modulation for acceleration stops. At constant speed, the inertial shielding, both for propulsion and for protecting the crew, switches off because it only works during acceleration. This means separate shielding would be needed for propulsion and for inertial, as also adaptable phase waveform control based on the current acceleration and velocity of the spaceship. Here you will find the papers I have released so far, brought to a satisfactory conclusion and which I do not plan to remove in the future. The last 3 were rejected by physics journals, and in the coming days I plan to submit the new paper titled Engineering the Leap to Inertial Warp Drives to the MDPI Aerospace Journal Special Issue on Breakthrough Propulsion for Spacecraft. This issue is guest edited by Martin Tagmar of Dresden University of Technology and Les Johnson of NASA's Spaceflight Center, with a submission deadline of June 30th, 2026. However, publishing is costly, and based on my experience and the many rejections I have already received the last 10 years, I doubt this paper will be accepted. Furthermore, I recommend a few resources that I think should be part of everyone's toolkit. I strongly suggest downloading the JLN Labs website for offline use. It's one of the richest collections of open experiments in alternative energy and propulsion technologies, and it's also one of the oldest sites on the web, dating back in 1997. You can also find me listed in the System G section as Ioannis Xydous. dating back to around 2003, sharing my analysis about the System G. It is an anti-gravity device from Professor Aquino. You can use Sciotech web copy or any similar tool to download the entire website while it's still online. I have already done this myself. I also recommend the work of Professor Aquino. Nearly all of his papers are experimental proposals in alternative energy and propulsion, and they can be a great source of inspiration both for those already working in the field and for new enthusiasts. Thank you for your attention.